Ma'am, your mic is off now.
Okay, good afternoon. So let's start off with where we left last week or 2 days back. So we had seen the magnetic field due to some current configurations. One was a straight wire carrying a current, and the final expression was important. What is the magnetic field for a long current carrying conductor if the distance at which we are talking about the magnetic field is small? We got an equation: B is equal to mu naught I by 2 pi d. Then after that, we talked about a circular loop of current. And then along the axis, we found out what is the magnetic field. We found that the magnetic field is given by the right hand rule. The curling fingers give the direction of the current and the thumb gives the direction of the magnetic field. Are you able to see? Because there's a power cut at home. I hope there's no disturbance.
Yes, ma'am, we can see.
Fine. Okay, so then here again, we are interested in what happens at the center of the current loop. Okay, so when we did that, we got an expression for the current at the center of the current loop, of the magnetic field at the center of the current loop, and we got an equation which said that the magnetic field is falling off as 1 by, sorry, we found that the magnetic field is given by mu naught I by 2r, where r is the radius of the current loop. Then after that, we found the magnetic field due to a part of a circular loop. Okay, and once we were done with that, we tried to find out what happens if the current loop is very, very small radius and the distance of the point P is very large in comparison. We found that the magnetic field is again given by the right hand rule, but then the magnetic field falls off as 1 by cube of the distance. And this reminds us of another entity where the electric field was falling off as cube of the distance, and that entity was called the electric dipole. Therefore, we call this small loop of current as magnetic dipole. More about magnetic dipole we will be seeing in the next few days. So now let us look at two parallel current carrying conductors. Okay, and then look at what is the net magnetic field that they will set up. So here for our discussion, we have taken two wires, okay. The wires are here, please. The wires are here carrying a current I1 and I2. And you can see that the current in one case is both these wires are perpendicular to the plane of the screen. And you can see that in one case, in I1, the current is coming out of the screen, and I2, the current is going into the screen. So please, this convention, you must understand, both these are parallel to each other, but the currents are anti-parallel. I1 is coming out of the plane of the screen, and I2 is going into the screen. We take a point P at a distance R1 from I1 and R2 from I2, and we want to find the magnetic field there. So the first thing that you should remember is that, like electric field, magnetic fields also obey the principle of superposition. Okay, so what we have to do is individually find out the magnetic field because of the first wire, get the magnetic field because of the second wire, and simply vectorially add them up. Okay, so here what I would like to do is I want you to remember the expression for the magnetic field for a long wire. So B1 is equal to mu naught I1 divided by 2 pi R1. Instead of 2 pi D, I will write 2 pi R1. Okay, and the direction is given by the right hand rule. Similarly, the magnetic field due to the second wire is mu naught I2 by 2 pi R2. Okay, now comes the thing. How do you exactly use the principle of superposition? So what you do here is, for the first wire, the current is coming out of the loop. So what happens is I curl my fingers in a circle. I curl my fingers in a circle, the right hand fingers, and look at how the magnetic field will look at the point P. Basically what I'm saying is, you imagine a circle like this. Okay, the magnetic field is going to be tangential to the circle, and it's going to be like this. It's going to be tangential to the circle and given by this arrow. Is this point clear, guys? How I got this B1 direction? I'm just using my right hand rule. Similarly, draw one imaginary circle of radius R2 around I2. Again, use the right hand rule. Only thing is, in this case, my thumb has to go into the plane of the screen and then look at my curling finger. So when I look at what is my curling finger at the point P, I'll find that this arrow is going to look like this. This is the arrow. And please remember, magnetic field is perpendicular to the radius in both the cases. So here also it is perpendicular, here also it is perpendicular. Okay. Doesn't mean that B1 and B2 are perpendicular to each other. Doesn't mean that B1 and B2 are perpendicular to each other. Okay, now you have to add these two vectorially. B1 and B2, you have to add them vectorially. And another thing you please note down, you're seeing that B1 is less than B2 in my picture. Why is B1 less than B2? What could be the reason you think? In my picture, B1 is less than B2 simply because I1 could be less than I2. Doesn't have any other big meaning. Okay. Now, again, it will also depend on the distance R1 and R2. Okay, now let's apply the principle of superposition. For that, what you do is, now you have to vectorially add these two. So construct a parallelogram. Construct a parallelogram and connect these 2 points. So what you get here is going to be your B vector. Therefore, this B vector is going to be equal to B1 plus B2. Okay. If you understood this, you have to help me do the same thing for changing this current direction. Let me change the current direction. I want you to help me. Okay. So what we'll do is, so that our time is saved, we will keep I1 as it is. We'll keep I1 as it is. And then look at what happens to I2. We'll look at I1 as it is and then see what happens if I2 direction is reversed. Let's say I2 is also like this. So both the currents are parallel. So then what will happen to my B1? Anyone? What happens to my B1? Will B1 get affected because I2 changed direction? No, B1 is independent. Okay, so B1 remains as it is. Okay, but then look at B2. So this current is also out. So use your right hand rule. Okay, and you will see that I will have to draw a vector. I will have to draw a vector which is anti-parallel to what I have drawn here. So this is going to be by B2 now, because the current direction got reversed. Now let us see what is going to be the sum. The sum you have to get by applying your parallelogram law. Okay, and then draw an arrow connecting these two. So this is going to be my B. Just do this exercise and see. If you do this exercise, you will be able to do these kind of problems easily. Now then what can be the next thing? Next thing is I1 you change the direction, keeping I2 what I have kept, and see what happens. Similarly, keep I1 and I2 both into the plane of the screen and then see what happens. So you can actually play with these directions and get to really understand how to apply the principle of superposition. So that's what this exercise will help you achieve. Okay, now before that, let's also go try one numerical. So here is a numerical. I hope you're able to see this picture. I hope you're able to see this picture. Okay, so here you are given two wires. Two wires, again, perpendicular to the plane of the screen. Okay, I1 and I2. I1 is out of the plane of the screen. I2 is into the plane of the screen. And the separation between them is a distance A. A is the separation between them. See here, A is the separation between them. This is I1, this is I2. And then he is taking a point here, which is at a distance A by 2, which is at a distance A by 2. Okay. And then he's asking you to find out what is the net magnetic field at this point. So what do? For I1, keep your right hand finger out of the plane and then look at the direction of your fingers at that point. How will it look? This will be your B1 vector. So you get your B1 vector. This is your B1 vector. And you see that B1 is perpendicular to this distance. So how do I get this distance? This is a by root 2. This distance is also a by root 2. Okay, and this is a. Similarly, get your B2 vector. In B2, only thing is you have to do it this way because the finger goes into the plane of the board and then look at the direction of the curling fingers. So you get your B2. Okay, this is B1, this is B2. Now, you will be able to quite easily see that this is an isosceles triangle, first thing. And from the relationship between the lengths of the three sides, the hypotenuse is A. You will see that this is a right angle triangle. You're going to see that this is a right angle triangle with hypotenuse equal to A and the other two sides being A by root 2, A by root 2. Okay. This also means that B1 and B2 are going to be perpendicular to each other. B1 and B2 are going to be perpendicular to each other. And you're supposed to find out what is the net magnetic field. You're supposed to get the net magnetic field. So B equal to B1 plus B2. Just I have done in the previous case, I write my B1 as mu naught I1 by 2 pi D1. So D1 is A by root 2. Okay, let's fill in. I1 is 15 amps. So put it there, write the distance. So you're getting 80 micro Tesla. But when you're getting B2, even before you do the problem, you're able to see that I2 is greater than I1. I2 is almost double of I1. Therefore, B2 will be more than double of B1. B2 will be more than double of B1 because the distances are the same, only the currents are different. Okay, now you have to add them. So to add them, because it's simply 90 degrees, you can simply get the magnitude by doing B is equal to under root of B1 square plus B2 square, okay, which is going to be 80 square plus 171 square under root, okay, then you get 190 micro Tesla. Okay, next thing is you got a vector, you've given the magnitude, you have to now give the direction. So to get the direction, you can see that the author has used this angle as phi and he's finding out phi. Now you may ask me, why should I take this angle? Maybe I'll take the other angle. You do it. The only thing is you define an angle and till the end of the problem, just go with it. Okay. So you can clearly see that tan phi from this triangle, you can see that tan phi is going to be equal to B1 by B2. Okay. So then you get phi equal to tan inverse of B1 by B2. Therefore, you get the angle as 25 degrees. So this is the way you use the principle of superpositions and find out the magnetic field due to two different sources. Okay? Any doubts? Okay, now let's try another. This should actually be easier. This should actually be easier. So here you have two long wires carrying identical currents I and I, but then the currents are anti-parallel. The currents are anti-parallel. Okay, two long parallel wires at a distance, A. So this distance is A. Okay, carry equal currents in opposite directions. Determine the expression for the magnetic field B at a point P on the line joining the two wires at a distance x from the midpoint between the two of them. That means this is your midpoint. At a distance x from the midpoint is a point P. You have to find out the net magnetic field at the point P. This is actually easier than the previous problem. The currents are anti-parallel. The first current is out of the plane. So because it is out of the plane, put your right hand fingers out of the plane and look at the direction of your thumb, of your curling fingers. The curling fingers here at the position P will be looking up, will be looking up. Okay, and both these currents are the same, that you have to remember, and this distance is going to be, if I call a by 2 as b, I will say that this total distance is b plus x. It's going to be b plus x, and the magnetic field is this. This is your b1. Similarly, I want to get my b2. So if I have to get my b2, what do? I put my right hand fingers, my thumb into the plane, and then look at how my fingers will rotate. I see that to the left, my fingers are going to look up. My fingers are going to look up. So what I'll do is I'll just put another color here. I get my magnetic field as this. This is my B2. And why have I put B2 greater than B1? My B2 is greater than B1 simply because the distance of the point P to the second wire is actually closer. Therefore, the magnetic field will be larger. It is closer to the source. Okay, now it's just two parallel vectors. We just need to add them up. So what do? Mu naught I by 2 pi d, I said. 2 pi b plus x in one case. And in the other case, it is going to be b minus x. This distance is b minus x. One second, I'll just come. I'm sorry. Okay, so now you just have to add two vectors. You can see mu naught I by 2 pi is going to be common. So pull it out. Mu naught I by 2 pi is going to be common. Pull it out. And then you have 1 by b plus x into, plus 1 by b minus x. Just take your, you can actually just do it. So it is b square minus x square. And at the top, you're going to get 2b divided by pi b square minus x square. 2 and 2 will go. Okay, so you're getting the expression. Or you can see that this magnetic field is going to be a function of x. Magnetic field, the net magnetic field is a function of x. So one could, just by using this equation, find out what is the magnetic field at the center. At the center, x is 0. Therefore, the magnetic field will be mu naught I by pi b. Okay, similarly, at this point, at any point, you can find out what happens when x is equal to 0, what happens when x is equal to minus b, what happens when x is equal to plus b. You could actually, get the magnetic field at any point between the two wires by using this one common equation. Similarly, you can also find out which is the point where this magnetic field is going to be a maximum. Where is the magnetic field going to be a maximum? Where is the magnetic field going to be a minimum? You can actually find out. So below this picture, you see a graph. This graph, what he has done is he has given some numerical value to a, I, and then x is the variable. So he has just tried to plot how it looks. You're finding that near the wire, the magnetic field tends to infinity. Magnetic field tends to infinity near the wire. Okay, on both sides. This is what you're finding here. This is what you're finding here. Now go beyond the gap between the two wires. Now go beyond the gap between the two wires and see the magnetic field. You will use right hand rule and you will be able to show that the magnetic field is going to look down. What I mean is here. Here, the magnetic field will be looking down. Both B1 and B2 will be looking down and you're going to get an arrow like this. No, I'm sorry. Your B2 will be looking up, but B1 will be so large that effective B will be in the downward direction. Use your right hand rule. I will just again explain this. Actually, these kind of questions can be asked in an examination. We can ask what will be the effective direction of the magnetic field at some given point. Okay, so First, let us take a point here. This is closer to the first wire, far away from the second wire. So for the first wire, use your right hand rule. You're going to get your magnetic field B1 downward. Now, at the same point, let us try to find out the magnetic field due to the second wire. The second wire is into, so you're going to get a magnetic field upward. Okay, but then the upward arrow is going to be small. Because the distance is more, the magnetic field value is more. Therefore, if you see what is going to be the net magnetic field, the net magnetic field will be in the downward direction. Okay, similarly, you can find out what is the magnetic field here. Here also you're going to find that the magnetic field is going to follow a similar trend. So that explains this part of the graph. And of course, this part is here. Okay. And from here, let us go to the third current configuration. The third current, please remember, currents need not always go in a wire. You can have currents even in a disc, in a plate. Okay, so what we are going to have here is a conductor. So it's a copper conductor. It's a copper plate of width A. Width is this. The width is A. Okay, and the thickness is negligible. So it's almost a flat conductor of width A. Let's assume that it's going to carry a current I. When I'm saying a plate is carrying a current, you have to remember that this entire region is carrying a current. So let the current be I. And the direction of the current is here. It's indicated like this. And let's assume it is a uniform current. Find the magnetic field at a point P. Okay, find the magnetic field at a point P at a distance R from the center of the strip along the perpendicular bisector. So what you do is, first of all, bisect this plate. Bisect this plate. Okay, and let's call this line as x is equal to 0. Then draw a perpendicular and at a distance R, take a point P, find out what is going to be the magnetic field at that point. Okay, so to do this problem, you have to again use the method of calculus only. You already know what is the magnetic field because of a wire. You know what is the magnetic field because of a wire. So let's use that. Imagine this entire strip to be made up of a number of wires of width dx and carrying a current di. Width dx carrying a current di, and let the location of that strip from the center be x. Okay. Now let's write the expression for the magnetic field. So let the magnetic field be dB because it's from a wire carrying a small current. Let that magnetic field be dB. So dB is mu naught I by 2 pi d. Normally that's a formula, but here you will write mu naught di by 2 pi d. Okay, di is that small current through that element. Okay, so mu naught di by 2 pi d. Now this distance d is actually x. Now you can show that x is r secant theta. Okay, I'm sorry, it's d only. It's going to be d only. Okay, the distance is d. The distance is d. Distance of that wire from the point P is d. Okay, and you can show that d is r secant theta that you are getting from this particular right angle triangle. Now you want to see how that vector is going to look. This vector is going to be perpendicular to r and d vector. Okay, so this is your db. You can see the db direction. Similarly, take another mirror element here carrying a current di with dx at a distance minus x. Okay, and find out what is the magnetic field of this fellow at the same point. You're going to get a vector dB like this. Okay, or in other words, you're going to get a vector dB from the first element and then a vector dB from the second element, and you can show that these two components will cancel out and what remains is 2 times this component. Okay, and this angle is theta, this angle is theta. Now we have come across so many of these again and again, so I don't think we'll get into all these discussions. Straight away, let's go to the result. Okay, you just do an integration. And how will you do the integration? You'll have to do an integration over x. You have to do an integration over x from x is equal to minus a by 2 to plus a by 2. Minus a by 2 to plus a by 2. And it is a cosine part of the magnetic field that will be surviving. Okay, so just do it and see. You will finally get the answer as mu naught I tan inverse a by 2r by pi a. Okay, just go through this mathematics. So this is the magnetic field. And what is interesting for this is what happens at points far away from the strip. What happens at distances far away from the strip. Okay, at distances far away from the strip, you're going to see that the magnetic field will become mu naught I by 2 pi r. Or in other words, the strip will not be seen as a strip from a far off point. The strip will be looking like a wire. Okay, this much if you know, that should be sufficient for you. Okay, but maybe you could even just try to find out what is this alpha. What is this alpha? Alpha is nothing, so we are just making a substitution here. X is equal to r tan theta, therefore dx is equal to r secant square theta d theta. Okay, so just make that substitution here. Finally, you're going to get the limits also to change. Limits will not go from minus a by 2 to plus a by 2. The limits will go from minus alpha to plus alpha, where alpha is given by this expression. Okay. Okay, now that we have finished discussion on the magnetic field because of a sheet of uniform current, now let us go to see what happens to two wires carrying currents. Two wires carrying currents. You know that a current carrying wire is the source of a magnetic field. That's what we have seen a few minutes back. Okay, so what happens here is, let's consider two wires, 1 and 2. We have two wires, 1 and 2. They are parallel to each other. Let them carry currents I1 and I2. Let the currents be parallel to each other. Let the perpendicular separation between them be D. D is the perpendicular separation between them. And here you can interpret it this way. I becomes the source. Current I1 becomes the source. You can do it the other way also, but we are just going to fix I1 as a source. So what will I1 do? I1 will set up a magnetic field at the position of I2. I1 will set up a magnetic field at the position of I2. And this magnetic field is going to be B1 given by your right hand rule. The magnetic field is going to be B1 given by your right hand rule. Okay. And what is B1 going to be? B1 is mu naught I1 by 2 pi D, the direction given by the right hand rule. Okay. And now B2, go to chapter number 32. Go to chapter number 32. A current conductor in a magnetic field experiences a force. A current conductor in a magnetic field experiences a force. So what is that force? Let us see. That force is F21. F21. What is the convention? Force on 2 because of 1. F21 means force on 2 because of 1. Okay, you know the equation for that force. It is IL cross B. IL cross B. What is I? I is I2. Because the current that you are placing in that magnetic field is I2. And what is the length? Length is L. And what is the magnetic field in which you are placing the wire? You are placing it in the magnetic field of the first wire. What is the magnetic field of the first wire? The magnetic field of the first wire is B1. Okay, just put them. And you are right away able to see that L and B1 are mutually perpendicular to each other. Therefore, the force becomes I2LB. Sine of 90 is 1, so I2LB. So next what you do is, you just have to substitute your B1 here. So you write I2L. Instead of B1, you will write mu naught I1 by 2 pi D. Okay, or this becomes mu naught L I1 I2 divided by 2 pi d. So this becomes the force. Okay. Next, what you do is, what is the direction of the force? How do I get the direction of the force? We have to use the right hand rule. So it is IL cross B. L B. L cross B. So the force is towards the second wire. Towards the second wire. Or the second wire is attracting the second wire is being attracted by the first wire. Now, you can do it the other way also. How do you do it the other way? The other way will be, consider the second wire as a source. So second wire will set up a magnetic field B2 at the location of the first wire. And because of that wire, there is a force on the first wire. That force will be F12. And you can quite simply show that F12 and F21 are equal and opposite. Okay? Or in other words, you are able to see that parallel wires, parallel current carrying wires will interact, they will attract, and anti-parallel currents will repel. So this comes from a combination of the concepts of chapter 32 and chapter 33. The only thing here is you can go one more step. You can talk about what is the force per unit length. They have taken L as the length of the wire. You can find out what is force per unit length. Force per unit length is going to be F12 by L. So when I do that, I'm going to get mu naught from this expression, mu naught I1, I2 divided by 2 pi d. Okay? Or one can ask questions like this. Okay, this is how we actually make questions. So look at this equation here. So the force per unit length between two parallel current carrying conductors is decided by A, the current in the first wire, B, the current in the second wire, 3, the gap between them, 4, the length of the wire. 4 options. But I've already asked you current force per length. So length is not the answer. So what are the answers? Current in the first wire, current in the second wire, the gap between the wires. So this is how we actually make questions for examinations. Okay, we just most often, sometimes, okay, let me be frank, sometimes what we do is we just lift some question from somewhere, make some small changes. But then when we need a lot of questions, this is what I normally do. I just open my slide, keep it there, and just go through the concept. Okay, and then, okay, so I can do one thing. I'll give you a current, and then this is the direction of my current. I'll take a point P. What is the direction of the magnetic field? East, west, north, south. You have to answer. Or the current is given by the right hand rule. Like this, we can ask. Or what is the force on the current carrying conductor? The direction of the force is given by the right hand rule. Then the force is directly proportional to the length. Force is proportional to the current. Force is proportional to the magnetic field. So these are all multiple answer. Multiple answer questions we are not getting anywhere from outside. All the multiple answers, obviously, we have to make. 90% of the questions we make on our own. Okay, so today I've given you that stuff also on how we make questions. So when you open a slide and look at it itself, if you're a smart student, you can actually guess. But then some of you are smarter. You don't want to waste your time doing all that. You prefer to either Google or ask your friend who is also a Google. And that's called copy. Okay. Now, how do you define an ampere? Please remember, when Coulomb actually performed the Coulomb's law experiment, the charge was not measured at all. There was no way by which charge could be measured. The unit of charge was not Coulomb. Obviously, say Rajiv Gandhi Airport is there. Rajiv Gandhi Airport was not named by Rajiv Gandhi. He died, and after that it was named. Okay, so like that, here also what happens is Coulomb actually does an experiment without having any unit for charge. So all he knows is he can charge a body by rubbing. So he gets a pith ball, he charges it. He gets another pith ball, which is identical, gets them into touch with each other so that, there is a charge transfer. Then after that, he conducts the experiment. And then he takes a third pith ball. He makes this charge half or quarter of the original. So he keeps on doing experiments like this. Similarly, when experiments were being done on the current carrying conductors, and the forces between them also, ampere was not known. Ampere was named after ampere. Similarly, coulomb was named after coulomb. Okay, similarly here, let us look at how you define what is an ampere. So for two long parallel wires of negligible circular cross section separated in vacuum by a distance 1 meter, ampere is defined as the current in each wire which would produce a force of 2 into 10 to the power of 7 Newton per meter length of the wire. 2 into 10 to the power of 7 Newton per meter length of the wire. To explain how that comes, let's look at this. Right hand side is mu naught. Current is 1 into 1 divided by 2 pi 1. So which is going to be 4 pi into 10 to the power of minus 7 divided by 2 pi. So what is the answer you're getting? 2 into 10 to the power of minus 7 Newton is the force per length. So this is how 1 ampere has been defined. One could have asked a question on that also. Okay, now let's see this. So now you know that if you have a current carrying conductor, you can apply a force on this current carrying conductor in any direction you want by applying a suitable uniform magnetic field. Okay, so this is the principle we are going to use for this numerical. So the numerical goes like this. You have a long horizontal rigidly supported wire. Rigidly supported wire. The wire is straight, it is long, and it is supported. And it is horizontal. And it is going to carry a current IA. IA is equal to 96 ampere. Okay, and then directly above it and parallel to it is a fine wire. Directly above it is a thin wire. Okay, that carries a current IB equal to 23 amperes, and the length, the weight per length is given as 0.073 Newton per meter. 1 meter has got a weight 0.073 Newton. That's what it means. How far above the lower wire should the second wire be strung if we hope to support it by magnetic repulsion? If we hope to support it by magnetic repulsion. So that means this should experience a force in the upward direction. So IA is going to set up a magnetic field at the location of IB. Okay, so from the picture given here, can you guess the direction of the magnetic field? Will it be into the plane or out of the plane at the location of IB? It will be out. It will be out of the plane. Therefore, I will show my magnetic field like this. At this location, this is how my magnetic field is going to be. I'll call this magnetic field as B because of wire A. Okay. And now, can you guess whether the current in the wire IB should be to the right or to the left? Parallel or anti-parallel to the first one?
Anti-parallel.
Anti-parallel. It should be anti-parallel so that there is a repulsion. It should be anti-parallel so that there is a repulsion. So the repulsive force should be acting like this. It should go up. Okay. And we will talk about force per length. We will talk about force per length because we know that there are actually now two forces acting. One is going to be the magnetic force per length, and the other force that is going to be acting is going to be mg per length. Now both these, if they are going to be equal and opposite, this wire can be balanced. Okay, so let's do it. So you can let this distance between them be d. Okay, so what do you first do? You just write mg by L is going to be equal to FB by L. For FB, you already got the expression. Do you remember? It's mu naught IA IB divided by, how much is that? Divided by 2 pi D, let us say. Okay, and then of course, force per length. So L is gone. And mg by L value is given to you. So that's given as 0.073. You know your IA, you know your IB, you have to get your D. Get your D. So you will find the D is equal to 6 mm. So if there is a gap of 6 mm between the two wires, then the magnetic field that IA sets up is sufficient to give an upward force and balance the thin wire above it. Okay, so in the next class, what we'll do is we'll start off with the third configuration of current, that is going to be a solenoid. A solenoid is by far going to be the most important part of the discussion, because in a real laboratory, in a real life situation, you use a solenoid to create magnetic field. And what is a solenoid? Solenoid is simply a spring of current. It's a wire which is turned in the form of a spring like this, maybe tightly wound spring. And where all do you find solenoid? You find solenoid even in an electromagnet. We have been talking of electromagnets. In some 2 experiments, we talked about electromagnet. One was your, what was that experiment? Your Hall effect. And then there was also, in Stewart Geese also, you had a magnetic field because of a coil. Okay, so the next class what we'll do is we'll discuss the magnetic field because of a current carrying coil, what is called as a solenoid. And then once the solenoid part of it is over, then we'll move to Ampere's law. Okay, so I know I could have taken class for another 5 minutes, but then I know it's saturating, so we'll stop here. Okay, meanwhile, I don't know how many of you noticed that in our WhatsApp common physics group, I have put a small message for the students. Next week, please hang around. You'll be able to see your corrected marks for all the 8 experiments. Okay, so that forms your internals, and then there will be one external examination. External examination meaning one multiple choice examination will be there, which will test all the theory that you have, everything that you have studied. Okay, that will be at the end of the semester. But then what you got, 50% of the marks will come from whatever you have done till now. So those marks will be announced to you next week. And I know that there are around 40 students who have not bothered to come to the lab. I don't know what they are thinking. They are not coming to the lab. But then just to get rid of the 40 students, we are going to give one more opportunity. You people can use the next 1 week. We'll open the window, close the window. We'll give you 1 week. Whatever you want, you submit. No classes will be taken for that, because we have already done. We have shared the materials. Interested students attended the class. You make a submission, but obviously you will not be graded like the others. Your marks you will get will be less, but then you won't have to repeat the subject. That much we will ensure. That is if you submit. If you don't submit, not even that. Okay? Yeah, so with that, I'm stopping. Anything else you want to ask? Yeah, as usual, you won't have anything to ask because you're all great people.